the Hall effect. Before I talk about what this is, there's one principle that you guys need to remember. When you have a current or a charge moving in a magnetic field, what happens? You have a charge moving in a magnetic field, what happens? It feels a force, okay? We need that concept today, all right? Because the Hall effect relies on this whole thing of there being a force and so on. Okay, so what I have here is a circuit, okay? And the circuit, you can call it, you can make it like this. There it is. That's the positive end. There's a negative end. Like that. Okay? Forget about the black part for now. Think of it as a very simple circuit. The only thing different that you're going to notice from this circuit and any other circuit is that instead of it being a wire all throughout, there is an entirely conductive plate at one section of the wire. Okay? And so the current's going to come around here and it's going to pass through the plate and then come around back and finish the current. All right? If there is no magnetic field, this behaves just like a wire, right? So the current's going to come here. There's going to be a high voltage, and then here there's going to be a low voltage. And so it's going to, the charges are going to move from high voltage to low voltage in a straight line. It's going to look like this. And the current's just going to continue going. Nothing special happens. Okay? However, if there is a magnetic field, something happens. So here I've indicated there's a straight up magnetic field going upwards. Let's call it a uniform magnetic field, just so that we don't add any more variables. And so now that there's a magnetic field, what's going to happen to the charges flowing in the plate? There's going to be a force. Well, let's figure out which direction the force is. We'll need to use our right hand for this. All right, so we have thumb in the direction of the current, fingers in the direction of the magnetic field, and therefore it's going to feel a force into this direction. Okay? If it was just a wire there, then the wire might move a little bit. All right, but in this case, there's no wire there, and it's charges inside the wire that are really important. And so the charges inside the wire are going to feel a force. So what's going to happen is instead of the current going in a straight line, you're going to have a current doing this. Okay? So the current is going to curve outwards because it's going to get forced away from the straight line, from the magnetic force, but it's still being drawn into the low potential, right? So, that's where the lowest energy state is. So it's still going to want to go there. But by getting there, it will have done some kind of arc motion, okay? And that's also not that exciting, all right? Until you realize that by doing that, what you're doing is you're creating at this apex here, right? At this apex here, you're creating a high voltage local region. A high voltage local region there. And over here, because it's the furthest point away from that high voltage local region, it's going to be a low voltage local region. So across this plate, you're going to have a voltage drop. And a voltage drop is great because that's an electromotive force. You can connect wires to it and make it do stuff like go through a resistor. All right? That's fantastic because what I just did is I kind of cross-stitched two circuits together to function at the same time. All right? And the only thing I needed to do is apply a magnetic field in this region here. Now, why is this useful, you might ask? Who uses that door downstairs to get in the building? Should be everyone. Who's coming through the front? Should be no one. All right. So yeah, that door, you swipe your card. That's a magnetic circuit, right? So what you're doing is you're introducing a magnetic field with your card. You're introducing a magnetic field of a very special frequency and a very special strength. It's very unique to your card, right? And you're swiping it and you're introducing a magnetic field, activating this part of a circuit. right? Because remember, this part of the circuit, this one here, it doesn't work unless there's a magnetic field. So where's this magnetic field coming from in that case? The current. Is that cool? Right? You introduce a magnetic field, it causes a voltage difference here, activates the currents to flow through here, and then you can see some work being done at this resistor. And this resistor might be to unlock a lock or to do whatever you want it to do. Okay? This whole process is called the Hall effect. And it's just a kind of a clever way of using Ampere's law that we talked about last time. This is an explanation again, same thing. So there's a buildup of charges on the sides of the conductor, and that's going to produce a voltage between the two sides. So look, you're going to see that there's a charge building up here because there's a force in that direction, and therefore there's going to be, by association, if there's a lot of positives there, there's going to be a lot of negatives there, and therefore there's a voltage drop or voltage difference between these two. And they call this the Hall voltage. Okay? You guys are able to follow? It's a very clever device. I think it was worth it to mention to you guys. This is something that we're going to talk about. Yeah, Max. Yeah? The circuit is already there, right? Right? So this circuit here is already there, but there is no current in it until there's a magnetic field. All right? So you really is when you introduce the magnetic field, when you turn on a switch or you introduce a magnet, then because of this effect here, you're creating a current in this direction, let's say, right? And then that's going to make it go around, and it's going to go through the resistor. And the resistor is just, I call it a resistor, but a resistor could be a load. It could be anything. It could be a motor. It could be a light. It could be, yeah. No, it's not connected to the battery. Exactly. And the only thing that's powering it is the voltage difference across this bridge here, across the middle. That's the only thing generating any kind of motive force. Okay? So I was here and I was saying that I'm not going to talk about this because I'm going to talk about the next PowerPoint. Right? The same thing with this. It's about the same topic. We're going to call this motional EMF, and we need to know a little bit about magnetic flux. Okay. Any questions on that? Because I'm about to move on. That's it for Hall effect. No? Great. Okay. Take out now PowerPoint number 27. We're going to talk about induction. All right. So induction, the term induction is actually quite important. Just how it's created. And before I talk about that, I just want to mention that this lesson we're talking about induction. Next lesson we're talking about inductors, and the lesson after that we're talking about inductors again. So this is an induction unit, and it's actually the last unit of the course. So you guys are almost at the end. This is officially the last unit of the course. It's not an easy one. That's why there is this symbol here of mass confusion. I don't know if you guys remember, but I had this when we did Gauss's law. Yeah. But you know what, though? I taught it now. This is the third time I'm going to teach it because I taught it to group 1 and group 2, group 1 and 3. And when you've already done Gauss's law, it makes this a lot easier. It does really make it a lot easier. If I were to teach you guys this first, then it would be really, really complicated. But it's not that complicated, promise. Now, why is it not swiping? Go. All right. So there's two laws that excuse me. There are two laws that we're going to talk about today. They're called Faraday's law and Lenz's law, right? And they're both describing induction. All right. They both have to do with induction. I'm going to explain them separately. First, we're going to do Faraday's law. It's actually quite simple. The idea of it, mathematically, not so much. And then we're going to do Lenz's law, and that the concept is a little bit abstract and it requires a lot of practice. All right. So we're talking about induction, and when I say I want to induce something, have you guys ever heard of inducing labor? in the medical terms? So someone who is supposed to give birth and they're very late in their labor and it's time to go and you don't want them to keep the baby inside, so you give them some medication to start contractions and to induce the baby's delivery. Okay? So what you do is you cause it to happen. So when I talk about induction, I mean the same thing. Now you're doing something to cause a current to happen. All right? So I'm inducing a current, I'm inducing a voltage, I'm inducing this whole thing from happening. Just keep that in mind as we talk about this. There's a couple ways that I can do this, but it all builds up into one idea, and that's the change of flux. Okay, and then flux is that term that scares you guys because it reminds you of Gauss's law. But I promise you, the second time it's easier. So let's talk about that. I'm going to come back to this, but I want to just highlight this one paragraph here. Okay, so if I want to induce a voltage, what I absolutely need to do is get a change in flux. Okay, a change in flux or a change in magnetic field. Those two are going to be synonymous. I'll explain to you guys why in a second. Okay, but the point is that it has to be a change, and that term change, or the rate of change, mathematically, what does that remind you of when I say change? Mathematics. Which way? Difference. Okay. The opposite of integrals. Derivatives, which is the difference, is also another way of saying different. So yeah, derivatives. So we're going to have to find the rate of change of things. And you can imagine that there's going to be some calculus involved. All right, so magnetic flux. This is the first thing that we need to get out of the way. If you guys remember, flux was described by this symbol here, and this is the Greek symbol phi. We used phi to describe electric flux, but now we're going to use phi sub b to describe magnetic flux. Okay. Flux is the exact same concept. You guys remember what it was in an electric field? An electric flux? Someone, can you describe it to me? Yeah. Absolutely. Okay. It's the amount of electric field passing through an area. So if I'm talking about magnetic flux, what am I doing? What am I talking about? Magnetic field passing through an area. Exactly. And so if I have some kind of, you saw that symbol though, some surface integral, right, of every single magnetic field with a dot product at every single little area of the surface, then I can get flux. Okay, this is the only difference between what I'm showing you right now and what you saw in Gauss's law is that instead of a B there, I had an E, right? It was just electric field, right? And we said that if we were smart enough to choose a Gaussian surface that was uniform, so that the electric field was uniform everywhere and was constant, and it's not variable. When something is constant and not variable, you can take that out of the integral. So you can say that if the magnetic field is constant, then you can say that it's a constant, and you can take that out of the integral. All right. And of course, now I'm just left with a surface integral of an area. Well, that's easy. The integral of an area is you add up all the small areas to get the big area. So we're just back at B dot A. Okay? And this is a dot product, similar to when we did Gauss's law. Dot product. And if you guys remember, so maybe you guys can now remind me again, when you did Gauss's law, how did you maximize the flux? What criteria did you need to meet in order to maximize the flux? Sammy, what needs to be perpendicular to what? Okay, so the surface had to be perpendicular to the field lines, but that meant that which vector is important for the surface? It's the area vector, and the area vector is a normal vector from that surface. So in fact, what you want is for these two to be parallel. You want the area vector and the magnetic field vector or the electric field vector, you want them to be parallel. And if they weren't, what relationship did you have to use in order to calculate the flux? You guys remember? Sine of theta? Is it sine or cosine? It's cosine, right? And then I'll remind you why. So now we're back to magnetic flux is equal to B times A cosine theta, right? And if they're parallel, if B and A are parallel, what's the angle between them? The angle between two parallel things is 0. And what's the cosine of 0? 1. Okay, so we know we did it correctly. All right. If it was 90 degrees to each other, if the area vector was 90 degrees to the electric field vector, what's the cosine of 90? It would be 0. In that case, there is no flux. Okay? You guys remember this? See, it's not so bad the second time? Correct. But what needs to be at 90 degrees? So do you remember? All right. So if I have a magnetic field like this, and that's my area, what's the angle between them right now? It is not actually, because you have to take into account that there's a normal vector coming out of the surface. It's the angle between the two vectors. Okay? Magnetic field, exactly. All right. Couple of things to add though that are new. One is the units for flux. Now we're going to talk about these units called Webers. All right, WB. Please don't confuse that with W's. What's the unit W? Oh, good, very. And you can also use Tesla times meter squared. It's the same unit, right? And it makes sense because it's magnetic field multiplied by area, so therefore Tesla meter squared makes sense. Okay? All right. Let's draw some parallels. Haha, get it, parallels. Between these two. They're essentially the same thing. You can see the similarities. It's just replace magnetic field with electric field. As simple as that. Okay? All right, now, Faraday's law dictates the following. This is very, very, very important. There is a production of an EMF. All right, we need to know this term EMF. It's electromotive force. And an electromotive force is the same thing as a voltage. You already know this one. It's just a new name that we're giving it. Okay? So what you can do is you can induce some voltage, all right, by measuring the change in flux as a function of time. All right, so there you go. There's your E induced, or your V induced, or however you want to call it. It's going to be equal to, oh, what happened there? It's going to be equal to the change in flux as a function of time. Okay? Or with respect to time, if you want to think of it in differential. Okay, so the change of flux with respect to time. Yeah. That E induced is the EMF, exactly, or the voltage induced, or however you want to think of it. Okay, so that's great because we know a little bit about flux already. So it's going to be the change in flux, and we have to now find a way to see how we can measure the change in flux. And there's many ways that we can change flux. Let's talk about a few of those ways. By the way, just so you know, this is called Faraday's law. The fact that changing a flux as a function of time is going to generate an EMF. Okay, there we go. Okay, first example. This is called motional EMF. You don't need to know the term so much as you need to know the concept. So imagine here, this is even holding the pen. There we go. All right. You good? You good? You good? All right. Imagine the following. There is no battery here at all. Okay, so remove from your mind that there is any kind of external energy source right now. Okay, there is a wire here, and this wire is exactly this size. All right, it's not connected, it's not going on to infinite to be connected to anything. What happened? The voodoo doll, yeah. Did it move? So imagine this wire just stops here, and it doesn't go on for infinity, and it's never connected to anything, right? And there's a resistor connected in that wire right here, indicated by the letter R. And there's no current in it, right? At least not yet, right? And what I have here is this bar, which is also conductive, all right? And this bar can slide back and forward, kind of like a trombone. You guys see a trombone? You hold it like this, you slide it back and forth. Yeah? Okay, so imagine that this bar here can slide back and forth. Still, nothing has a current in it at all. If you have magnetic field going downwards, as indicated here, and this is a uniform magnetic field, all right? And I have this really, really close here, and I start sliding it, what's happening to my flux? So hold on. So I have my bar here, and I'm moving my bar here towards the right. So what am I increasing? The area, right? So if I'm increasing the area, is my flux changing? Yes, even if my magnetic field is remaining constant, my flux is changing, right? So it's changing. Is my flux increasing or decreasing? Increasing, all right. So that means, okay, I'm increasing my flux. And as Faraday's law says, that as you increase the flux, you generate a current, you generate an EMF. So that means now, inside this loop that's completed by this rod here, so it can go like that, there is a internal voltage that you just induced. And when there's an internal voltage and there's a resistor in play, then that means you're going to have an induced current. All right. So imagine that. You just created a circuit, all right, with nothing, no battery, nothing, and all you did was move left and right this bar. Okay? No battery, no plug, nothing. All right. So I'm going to call this bar. Ugh. My pen is going crazy today. I'm going to call this bar. And as the bar moves, then flux is changing. So flux changes as a function of the bar's position. Therefore, EMF is induced. Okay? We don't know which direction that is. I gave it some arbitrary direction there. I said that I is going in that direction. But what we need to do is use Lenz's law, which we haven't looked at yet. We need to use Lenz's law to figure out which direction it's going in. That's coming up in the second half of today. Let's not deal with that right now. Let's talk about that EMF that we just induced. It sounds like someone's playing the tambourine. I don't know who it is. Stop that. So we know that E induced is equal to the change of flux with respect to time. This is Faraday's law. Okay? We also know that the flux is a product of the magnetic field and the area. And in our problem here, everything's at 90 degrees, so I don't have to worry about the angle. Okay? In my loop here, let's say I redrew my loop. Here's my loop. This side has a side length L, right? And this is a bar that has a variable position S. How could you express my area of my loop? Pretty simple. S times L, or L times S. So I can replace that here. So phi is going to be equal to the magnetic field multiplied by L multiplied by S. S is a variable because as you slide the bar along, it changes its position, and so S is changing, of course. All right, so that means I can rewrite my equation here. I can write that E induced is equal to the derivative with respect to time of, instead of flux now, I'm going to write down B times L times F. Now, which of these three variables are constant? Or which one of these three expressions are constant? E and L. So I can take that out of the derivative. So E induced is equal to BL ds by dt. And what is ds by dt? What is the change of position as a function of time? Speed or velocity. So that means that E induced is equal to B times L times V. So, okay, so that means that the amount of, I gotta go back now, if I change this thing, right, if I do this all along, I'm changing it for sure, but if I change it really quickly versus really slowly, which one's gonna produce a higher EMF, quickly or slowly? Quickly, exactly, and we just proved it here because V as an expression is directly proportional to our EMF induced. So if we increase V, then we must increase the the induced field, the induced motive force. Now, so you can do this quickly or do it slowly. You're still going to get an induced current. You'll get a stronger induced current if you spin it faster, if you move it faster. Okay. So far, so good. Keep in mind, the main thing that you need to understand right now is that a change in magnetic field, or forget it, a change in magnetic flux induces an EMF. Okay? And you can change the magnetic flux in two ways. You can change it by changing the area, or you can change it by changing the magnetic field. Why do you go faster? Because now your change of flux is greater, right? So you all of a sudden allow a whole lot of magnetic field lines coming in. Your delta magnetic flux is really high. And because it's the EMF is the change of magnetic flux, the function of time, then your EMF is going to be higher. Yeah. The bar is changing the area because the area, if we go into my drawing here, the area is L times S, and S is the position of where my bar is. So if I move my bar here, my S is going to be smaller. And if I move my bar here, my S is going to be bigger. Yeah, and the area is this. The current is going to go where the bar is, because the bar is also conductive. Okay, so the circuit is made by the bar and not wire. Yeah, Laura. Same thing, except the current will go in the other direction. Because it's just the change that matters, not the quantity. So if it goes from a really high magnetic flux to a really low magnetic flux, the change is the same as if you go from really low magnetic flux to really high magnetic flux. It's the delta that matters. The current will go in the other direction. Okay? Okay. So here it is. Yeah. What's a vector? Yeah. All right. I'm not going to solve this question yet because we need to use Lenz's law. It's asking you about direction. Excuse me. Close viral cough. But imagine this. I have a loop here. It's just a square loop, not connected to anything. And it's going to approach this magnetic field. The magnetic field is pointed towards you or away from you? Towards you guys, exactly. And so is there a change in magnetic flux as I bring this closer in? Exactly. So as I enter this, the area entering the magnetic field is increasing. So therefore, there is an increase in magnetic flux. and therefore, yes, there's going to be an induced current. That question's asking about direction, but we're not there yet. But you could answer this one, all right? So I have a triangle that I've placed, and this triangle does not change in size, right? And it's standing in a magnetic field, right? And the magnetic field, it says in this question, is decreasing from 0.3 Tesla to 0.1 Tesla, and it's taking 50 milliseconds to do that. Is there an induced current, yes or no? All right, so that means we should be able to calculate it. You guys go ahead and do that. Oh, I wrote E, but it's actually B. Yeah. So right now you're not moving it.
Yeah, but
Okay.
when you're moving the bar,
Yeah.
you feel neutral,
Yep.
and there is energy.
Yep.
Yeah, and does this energy comes from kinetic energy, or
No.
so where like it can just appear?
It comes from the flux. So the magnetic potential energy.
Okay.
Yeah. Oh yeah. Um, You guys have an answer? 0.08 volts. A. So let's recap, please. What are the two ways you can change flux? Area and magnetic field. Magnetic field. Okay. You can change the magnetic field or you can change the area. All right. Okay, answer this question for me. I want you guys to rank these from lowest to highest or highest to lowest, however you want, in terms of magnetic flux. Right? No, you can't. It's an awkward classroom. I think. Yeah. Explain to me what's happening in the third one. Sorry, the fourth one. Yeah. You take which part of the loop? Yeah.
Even though it's not like over the whole area, you still have the same number of improvement as possible.
Okay, so which area do I use? Do I use the full area of my loop or half the area of my loop? Well, it does change because you can't increase the area. If you increase the area, you're increasing the flux. So it does matter.
Let's say it's half enters.
Okay. So you have to consider which area has a magnetic field. It can't be any
It
area.
would be 1/10.
Exactly. So in fact, I have to find the area, the half the area. Guys. So it would be in this case 2 multiplied by 1 times 1 is equal to 2 units of magnetic flux. So the answer would be A is greater than B is equal to C is equal to D. Okay, let's get to some harder problems now. So, that was very easy. All right, so here I have a problem where I have a loop, a circular loop, in a magnetic field. Now my magnetic field is not a constant magnetic field. It varies as a function of time, right? And so I have a loop and the magnetic field is going to either increase or decrease, but it doesn't matter because it depends on time. It just changes as a function of time. Therefore, I know that for sure there's going to be a voltage induced in this circular loop. Now, it's telling me to find this EMF, this voltage induced, at time is equal to 6 seconds, right? And we know that I need to find the change in flux, all right? So what do I need to do in order to find the change in flux? Yeah, exactly. I have to take the derivative to find the change in magnetic field. Because remember, there's two ways that we can get a change in area. In this case, the area is not changing. So I need to figure out that there is a magnetic field change. So that means I need to find B. Oh, I need to change colors. What I need to find is B prime of 6. Okay? That means I need to find the derivative of my B function. So in this case, you can use the chain rule. If you can do this in your head, you can. It's not a hard one. The chain rule for derivatives, it's that the function itself multiplied by the function inside. The derivative of the outside multiplied by the derivative of the inside. That's what the chain rule is. Yeah? That doesn't ring a bell? So in this case, if I do the derivative, I end up with minus 20 e to the power of minus 2t. That's my, when I derive with respect to time, what am I finding? The rate of change, exactly. Now I have my rate of change of magnetic field. So that's perfect because that's exactly what I need, because I remember that E induced is the rate of change of my flux as a function of time, and that my flux is a product of my my magnetic field. So it's going to be area, which is constant, multiplied by dB over dt. Okay, well that makes sense now, because all I need to do is going to be my area, which is constant, multiplied by my new function. Oops, sorry, go back. Multiplied by b prime of 6. Okay, now we're at the easy part. So area is equal to pi r squared multiplied by the this function here, 20 times e to the power of minus 12. Oh, minus 20, yeah. What number did you guys get for this? Ah, c'est le rayon de mon sac. Ah, c'est écrit dans la question. 1 centimètre. Oui, exactement. Can someone give me an answer for my voltage induced? Minus what? Minus what? Minus? That's the right answer. Okay, let me ask you guys a question. So I figured out that my voltage induced, or my E induced, is negative 3.8 times 10 to the negative 8. What are my units for that? It's not Webers. It's my E induced. It's volts. Okay? And the question's not asking me what's my E induced, in fact. The question's asking me what's my current. So now I need to just use Ohm's law, right? Which is V is equal to I times R, or V over R is equal to I. So that means I have my 3.8, the negative sign. We're not going to talk about it just yet because we need to know Lenz's law for the direction. Divided by R, and the R is given in the question, 0.10 ohms. So my answer is going to be 3.8 times 10 to the minus 7 amps. Okay. The minus, what's that? By plugging in the values for this. Okay? Oh, you didn't convert your centimeters to meters. The radius. Okay. That wasn't too hard, right? Okay. So now is the time I have to show you some videos. I just want to tell you something real quick before we change rooms, guys. Thank you. Lenz's law dictates that there is some kind of internal inertia to this. And do you remember what the term inertia meant when you guys might have learned it last? Did you learn inertia last year? Okay, what does inertia mean? It's the resistance to what? The resistance to motion, or the resistance to change of motion. All right, and that's the same thing here. Lenz's law is magnetic inertia, which we're going to learn about. Is going to be the resistance to the change in magnetic field. All right, so keep that in mind. We're going to take 5 minutes to move downstairs. Okay, let's not take too long because I want to end this class and I want you guys to go home early. So let's meet downstairs in 5 minutes in the room that we normally meet on Tuesdays. Guys, come on. Yeah, have a seat. Okay, we're gonna get started. Have a seat. Get out. Out. Felix, you're the last one. Please don't occupy yourself by this. What's this bozo doing now? Can we start? All right. Shut the front door. Thank you. All right. So this is just a demo about how it works, or sorry, a demo of Lenz's law in action. It's kind of hard to tell what's happening, so don't worry, the videos get more interesting actually. So the first one is the least interesting. Observe and be mind blown. All right. So let's hear what
Magnetic
happens.
braking is a type of braking
This
which
is called
doesn't rely on
magnetic
mechanical
braking.
pressure, as is common in most braking systems. We'll demonstrate this type of
Now, of course, there's no sound. Okay.
braking using a magnet and a copper tube. Unlike iron, copper is not a magnetic material, so the magnet won't physically stick to it. Braking is a type of braking which doesn't rely on mechanical pressure, as is common in most braking systems. We'll demonstrate this type of braking using a magnet and a copper tube. Unlike iron, copper is not a magnetic material, so the magnet won't physically stick to it. Therefore, a magnetic attraction cannot be the reason for any slowing in the fall of the magnet. A slit has been cut in the front of the copper tube so you can see the magnet as it drops. As you can see, the magnet falls much slower than you might expect. We can drop a non-magnetic metal through the tube and see how quickly it falls. It falls much faster. Therefore, magnetism must have a role to play in this process, even if the magnet is not being physically attracted to the copper tube. If we look down on the copper tube as the magnet falls through it, you can see that the magnet never touches the sides of the tube. Therefore, friction cannot have a role in the magnet's deceleration. Using the following cartoons, we can explain the processes that are actually happening. Again, we see the magnet dropping through the tube. The red lines are added to represent the magnetic field produced by the magnet. As the magnet falls, the magnetic field in the copper tube changes. This variation in the magnetic field induces an electric current, as predicted by Faraday's law. Faraday's law states that any change in the magnetic environment of the copper tube will cause a voltage to be induced in the tubing. This induced voltage creates electric currents in the copper called eddy currents. They're called eddy currents due to the circular motion they undergo. All electrical currents produce their own magnetic fields, which are illustrated in this diagram by green lines. Another law predicts the direction these induced electric currents and their magnetic fields will flow. This is called Lenz's law. Lenz's law states that when an electromagnetic field is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced electromagnetic field is such that it produces a current whose magnetic field opposes the change which produces it. Essentially, this means that the magnetic field created by the eddy currents oppose the magnetic field created by the falling magnet. It is the opposition of these two magnetic fields working against each other which slows the fall of the magnet. This video from the MIT Physics Lecture Demonstration Group demonstrates magnetic braking using a copper pendulum. The pendulum swings freely when the magnets are not switched on. Once the magnets are on, the pendulum experiences a changing magnetic field as it swings. This changing magnetic field induces a voltage in the pendulum, which creates eddy currents. The magnetic fields created by these eddy currents slow the pendulum to a stop. This perforated pendulum contains many gaps, and these gaps are occupied by air, which has a very high resistance to electrical currents. Weaker eddy currents means a weaker opposing magnetic field. This results in less magnetic braking or damping, and the perforated pendulum comes to a stop much more slowly than its solid equivalent.
Okay. This third one is actually my favorite. Magnetic metal. So it shouldn't do it with a magnet, so that thing in the middle of the magnet. No. And finally, have you guys ever heard of Veritasium? Yes, this is a video from them. More kind of fun to watch, but it does explain a little bit this whole phenomenon, and then we'll go over it.
I have a pipe.
Together.
Yeah. Do you want to hold it? Do you know what it's made of?
Metal? Is it brass? Copper.
Is copper magnetic?
No. Uh-oh.
I'm gonna go no, I didn't think it was.
I'm gonna go yes.
Yeah.
Well, why don't we check? This is a magnet, and I'd like you to use it to test whether the copper is magnetic.
No.
I want you to be 100% sure. Yeah. What do you think?
No.
It's not magnetic.
I said so.
Okay. Is there anything in there?
No.
What do you see in there?
That's nothing.
So why don't we drop something through it and just make sure it's empty, right? Okay, this is not a magnet. So this isn't a magnet, but let's see what happens when we drop it through. That was a dull experiment, wasn't it?
Yeah.
Okay, so what's going to happen if we drop this magnet down the pipe? It's going to pull through? Let's do it. 3, 2, 1.
That was weird.
That's well cool.
Took longer.
What's slowing the magnet down?
It's got to be magnetic poles or something. I don't know. North, south.
Something to do with the polarity of the north and the south poles.
But it doesn't stick.
But then it's not magnetic, so it shouldn't do anything.
Right, you guys saw that.
Inside,
That is slightly magnetic on the inside somehow.
It's going to be magnetic inside, isn't it, or something? Does it like...
It kind of suits.
I think it's the powers of the universe.
I don't know why it's doing it.
Well, this is what's exciting, is only a few blocks from here was the lab of a guy called Faraday.
In October 1831, he built the world's first electric generator here, a magnet which you push and pull in a coil to generate electric current.
So that's the actual...
Yeah, for world's first electric generator.
And there's a permanent magnet in the middle?
There's a permanent magnet, yeah.
It was Faraday who realized that it's a changing magnetic field that actually can generate electric current. So as the magnet is falling through the pipe, it's creating a changing magnetic field that generates little electric currents, so-called eddy currents in the pipe, and they create an opposing magnetic force on the magnet, slowing it down. So it actually turns the pipe into an electromagnet,
I see.
which pushes the magnet up. And this is what's known as electromagnetic induction. So it causes my LED to light up there. But it's important that you move the magnet quickly, because if you move it too slowly, the magnetic field is not changing fast enough to generate enough voltage to light this LED. This is actually the way all electricity is generated.
Is it?
Yeah, you move a magnet near a conductor and it creates electric current. But where is this electrical energy coming from? You can't get energy for nothing. Well, Faraday realized that there must be a force pushing back on the magnet. It's the same force that slows this magnet down as it falls through the pipe. So there's actually energy being converted from gravitational potential energy into electrical energy and eventually to heat. So this pipe is warming up by taking some of the energy out of the falling magnet. Is that any good or what?
Oh, it's very good.
This way. And these currents coming around this
I'm going to show you, what's behind you? I'm going to show you guys one last video. But I'm not going to show you the whole thing, I'm just going to show you part of it.
And as they change, we're getting change in magnetic flux, and so we're getting current inside the wire. Now, another way to look at this would be through a generator. And so in this setup, what I have is a magnet down here on a wheel. So
I'm just going to point your attention to a few things. This here represents charges in a conductor, right? Pay attention to what happens as this whole simulation is happening. Pay attention to this, direction of the blue thing, and the arrow which direction is pointing, okay?
so that I can spin that magnet. I have my wire again, and I'm trying to induce current inside that wire, and then I'm going to measure the amount that I'm going to change. And so watch what happens now when I start to turn on the water inside that faucet. It's changing the position of the magnet. As it changes the position of the magnet, it changes the magnetic field. You can see the magnetic field lines are changing, and so I'm starting to get a little bit of current. What happens if I increase the speed of that water? I'm getting more current. We can even have a light bulb connected to it, and so now I'm starting to get usable energy. Watch what happens as I increase the number of wires. I even have more energy coming out, and now if I increase the water again, I even have more energy being produced. And so we're taking that energy of the flow of the water and actually making electromagnetic energy out of it.
What happened to those charges in the loops? Yeah, they go back and forth, right? And the fact that they're going back and forth is very, very, very important. Remember, it's just a movement of charge from a low potential to a high potential that we're able to generate any energy out of. Remember, in the static electricity part, all that potential electric energy is from the movement of charges, right? Not from it doing a full loop, right? All the current has to do in a circuit is pass through a resistor, and it's already done its work. It doesn't need to reach the other side. All right, so if it goes in one way and it does its work, and it does the same work in the other way. And so what kind of currents is this? Yeah, this is what an AC current is. And what is this here? If we were to take what is that? That's a hydroelectric dam. It's a generator, right? So in fact, water is pouring down our rivers, right? And we've got these underwater. Right? Water is pushing and turning these really, really, really fast, or they're really giant wheels, and they're turning giant wheels really, really fast. And these wheels are wrapped in solid core, and that is actually directly connected from those dams into the the power outlets in these rooms and in your house. Right? So what we're getting is the back and forth motion of current, right? And that's an AC current because not all the currents coming in the same direction. Isn't that neat? All right, but now we have to do the hard part, which is tolerate that noise. We have to do the hard part, which is determining the direction. Okay, so again, I want to mention that Lenz's law is a law of inertia, and that basically inertia resists any kind of change. All right, so you want to increase its speed, inertia or nature is going to try to keep its speed low. Okay? You're going to try to increase the magnetic field, inertia is going to try to keep the magnetic field low. Okay, keep that in mind. So here's an example. Here's an example, and it says the magnet is moved downwards at a constant velocity. Okay, so that's what we're starting with. I have what I presume is a conductive loop. This would not work if this loop here was not conductive. Is this loop connected to a battery? No, it's not. All right, so a magnet is going to have field lines coming out of it. Now, of course, it's going to bug. Oh, wow. All right. All right. So that's the south end of a magnet. Which direction are the arrows should be pointing? Up or down? Towards the south, in this case, meaning up. All right. All right, let me ask you a question. If I move this magnet downward, so right now there are 3 magnetic field lines pointing through the loop, right? So that's going to be your flux. Is the flux changing, first of all? Is it increasing or decreasing? It's increasing, right? And there's going to be from 3 up arrows to what? 5 up arrows, right? So you're increasing it from 3 up arrows to 5 up arrows. Nature, they don't like that, all right? So nature is going to try to oppose that by putting an induced magnetic field. Which direction is the induced magnetic field going to be, up or down? Down, because it's increasing in the up direction. It's going to want it to be less up. So if it wants it to be less up, it's going to push an induced magnetic field downward. All right, I'm just going to draw it here in the middle. All right, I'm going to call this B induced. All right, now how do you generate a magnetic field? This magnetic field doesn't just come out of nowhere. How does it come up? What produces a magnetic field? We talked about this. It's Ampere's law. Last class, what do we do? Exactly. So there's going to be a current along this loop that's going to get induced in order to produce this magnetic field downwards. If I want to produce a magnetic field downwards, which direction does the current need to be in? Well, let's use our right thumb down. It's going to have to go like that. All right. It's going to have to go like that. Like that. All right. Because there is a law of magnetic inertia. It doesn't want the flux to increase. So it's going to produce an opposing magnetic field. So to balance it, to keep it balanced out. Okay. Now that was a doozy. Let's do it again. This time the magnet is moving upwards. Yeah. You're not increasing the current in any way. The current is increasing spontaneously. If the current gets bigger, you can, yeah, I guess if you have a current that's big enough, you can make it go upward. Yeah. Yes. The north falls down? Okay. We're going to do that example right now. Okay. After this one right here. So let's try to do this. All right. So right now, I'm going to draw my magnetic field lines. All right. And as in this thing, the magnet is moving upwards. So as I bring this magnet upwards, are there going to be, so right now there are how many field lines? 4. As I bring it up, are those field lines going to increase or decrease? decrease, all right? So there is 4 up, and then afterwards, let's say there is 2 up. So is it more up or less up arrows? Less up arrows. So nature doesn't like the fact that there are less up arrows. It's going to want more up arrows because that's what it's used to. So what is it going to do? It's going to give you an induced magnetic field in the up direction. And if you want to induce a magnetic field in the up direction, you stick your thumb up, you go around with your hand, and you see which direction the current goes. Well, that's easy. That's the easy part. We end up with this. Exactly. Okay, so initially, when it's close to the loop, there are 4 arrows pointing upward. As you make it further and further away, these arrows, these side arrows, let's say they don't fit anymore. They don't go into the loop anymore because they're spreading out. So there's only 2 up arrows when you move it up. So it went from having 4 up arrows to having only 2 up arrows. So there's less up arrows. Nature doesn't like that. So it wants more up arrows, so it's going to make its own up arrow. Okay? Yeah, so there's going to be a loop. There's going to be a current in the loop just to produce this magnetic field upward. It's the lowest energy state, right? So it's doing that because that's what's energetically favorable. All right, but that's why the reason why it behaves that way is to oppose that decrease in magnetic flux, right? So it's going to decrease. It's going to sense that the magnetic flux through the loop is decreasing and increase it artificially by producing in this induced magnetic field upward. Okay, let's do it again. Now I have a north-facing magnet going downwards in the loop. I told you guys I have a ton of these examples. I'm going to drill it into you until you figure it out. My magnetic field lines, are they going away from the N or towards the N? Away from the N. So I'm going to draw them like this, like this, like this. Initial situation, before I brought it down, how many magnetic field lines are going through the loop? Well, 2, because these ones are kind of going off to the sides. Only these 2 are making it through the loop. If I get closer, though, are they all going to go through? Yeah, so it goes from 2 down to 4 down. That means the downness of the arrows went increased, right? There's more down now. So then nature doesn't like that. So what is it going to do? It's going to produce an induced magnetic field upwards to oppose that. All right, so B induced is upwards. And if B induced is upwards, what could you tell me about the direction of the current? Is it going to, if you look at this from the top, is it going to be clockwise or counterclockwise? Counterclockwise, exactly. Yeah. It's not that it's good or not good. It's just that the law of inertia states that every law of nature opposes change, right? So it's, for example, you have a rolling ball coming towards you, a big rolling thing coming towards you. It's going to be really hard to stop it because it doesn't want to stop, right? And nature wants it that way. And so the same thing here. If the magnetic field line is a certain way, it's not going to want it to decrease. It's going to do its best to keep it from decreasing. So it's going to increase. Okay, yeah. Oh, good question. Okay, so what happens if now you're through here, you're in the middle, and now your magnet is falling downwards? It would be like this one, except it would be upside down, because now the south end is moving away from it in the downwards direction. Exactly. So it's going to switch direction. Okay? Forget about this picture on the left. Don't do it. All right? It doesn't mean anything because there's no. What's going on here? So the question is, indicate the direction of the current I. well, it's a solenoid now, so we have to use a different system. A solenoid. So by moving my magnet towards the left, am I increasing the amount of magnetic field lines? And I'm increasing them in which direction? In the left direction. So that means I'm going to have an induced magnetic field in which direction? The right. Now, if I know that, I got to use my right hand rule, but this time for solenoids. All right, so right hand rule for solenoids is thumb in the direction, and your fingers behind are going up. The fingers in front are going down. And since I see the front of my solenoid, I'm going to draw all my currents going down. So that's the direction of my current. Okay? And if they're going down, that means they're entering my ammeter in the negative direction. And by convention, that's going to give you a reading in the negative side of the. Let's try another one. Read the question. Try to do this one on your own. So my advice here is to draw une situation initiale and a situation intermédiaire, let's say, and a situation finale. Kind of like your incredibly boring essays you have to write in other classes. I ever tell you guys a story of why I came to hate English and French and all those essay writing BS classes? I was in CEGEP in second year, and I think it was my third or fourth semester, I don't remember. So I had class with my girlfriend then, and she actually became my wife. But I was fed up. All right, I never did well in this English class, and I worked really hard, and I never did well. And so one day I got fed up, and I told my girlfriend, I said, Yvonne, you need to write this essay for me. I got no more motivation. I'm done. And she's like, no, I can't write 2 essays. That's crazy. I don't have enough time. You write one of them, and then you just write my name on it, and I'll write one, and I'll write your name on it. And she's like a 90 student, right? And I was like, all right, if you don't mind bombing this one essay, I don't care, because I need this grade, and I've lost all motivation possible. So we did it, and she handed in mine, and with my essay, she got 90, and I got 65 with her essay. BS. I lost respect for all essay writing classes after that. Done for life. Yeah. All right. Back to reality. Okay. So initially, how many lines are going through my loop? All right. And eventually, how many lines are going through them? 3. So is the number of up arrows increasing or decreasing? Increasing. So what's nature going to do? It's going to give you a B induced in the downward direction. All right. So B induced in the downward direction is going to be, if we look at this from the top, it's going to be clockwise. And in the question here, it says a clockwise current is negative. Because automatically, I can discount A and I can discount C, because those show me that initially they go upwards, they go into the positive current, and that's not the case at all. All right. So now I have this situation, and this situation is showing me that I have 3 up arrows going in, and then here I have how many? None. So my upness, the amount of up arrows, is decreasing. So it's going to want to counter that by not allowing it to decrease. By doing what? Inducing it in the upward direction. Exactly. So that means now I have a B induced in the upward direction. You use your thumb, use your right hand. You know that it's going from the top view. What is it going to look like? If my induced is up and I'm looking at this from the top, is it going to be clockwise or counterclockwise? Counterclockwise, exactly. And if it's counterclockwise, that's positive. So that means that my answer has to be D, because at some point it has to be positive, and in B, it's never positive. Okay? I'm still not convinced that everyone knows what I'm talking about. So more examples, let's go. Which of these situations is true? You guys do it on your own. So I want you to write a T or an F underneath each one. You lost? Totally lost. We'll do these examples together, and hopefully I'll ask you, okay? But it's okay, I want you to understand. So Genevieve, I'm going to ask you for B, and Hugo, I'm going to ask you for C, okay? Because you also look very confused. In this case, yeah, I have the north end of the magnet going down. North end is downwards, and I'm moving it upwards. Okay, who wants to do A for me? All right, Gabrielle, tell me what's happening. So it's true, absolutely. Okay, Genevieve. Yeah, okay, very good. Are you understanding it? Hugo. Okay, but hold on. What direction are the arrows pointing to right now? Down the O. Okay. If I bring it down, are there going to be more arrows pointing up or less arrows? Yeah. If I bring the magnet closer, look, these two are not going in the loop. But if I brought it closer, would these two go in the loop or not? So then there are more arrows going upwards. Okay, so there's more up, and nature doesn't like that. So what is it going to do? Yeah. Yeah. Is that the right direction? Yeah. What's that? Well, it matters because it determines which direction the lines are coming in or out. Correct. But you have to know which direction it's going in. Who wants to do deep? Someone volunteer for deep. Okay, go. Okay. Okay. Yep. Okay, and is this correct? Yeah, absolutely. All true. All right. Yeah. Hey, sure. So right now, all the arrows are going down out of the north. That's the end. That's the north end of the magnet. All the arrows are going out north that way. If I bring it closer, there are going to be more arrows going into the loop. Right now, look at this one here and this one here. They're not in the loop. So when you bring it closer, those ones will be included. So you have more down arrows. Nature wants less down arrows, so it's going to produce its own up arrow, right? So if it produces an up arrow, that means the current has to be going in this direction. They're all true. We're going to skip this one because it's too similar, but I want you guys to do this one. No, I skipped it. It was too similar. Yeah. You want to give an answer? Okay. Read the, it's going in the center, but read the text, okay? It's explaining the text. The drawing is not very good. If you solve it in one direction, just figure doing the opposite is just going to result in the opposite result. Who wants to try and do this one? You've already gone, so I want to make someone else stress out a little bit. You've already answered. But I like that you know the answer now. Keep your answer and we'll see if it works out. I'm going to go for the quietest kid in class. Robert. All right, so everyone has to be quiet because I already have a hard time hearing Robert. Right. On va voir, disons, dans le tableau ou sortant du tableau. Dans le courant va aller vers la gauche. Clockwise or counterclockwise? Counterclockwise, okay. Okay? Yeah, and when you do the opposite of what you just said, then it's going to behave in the opposite behavior. So it's going to go in this way, and then when you remove it and then you pull it back out, it's going to go in the opposite direction. I think you guys understand this. Let's do this. Next class, we're going to do more hardcore examples. Have a great day. Come to the board, because then we can draw on it. They're going to be in the circle. That means there are more up arrows after the final situation. Or more up arrows. So they might have the word more up nature is going to provide some time.
I saw my grade on my exam. I know that you showed this last year. Is it possible to become scholars or?
Yeah, absolutely. You'll come down.
Yeah. Can I just go get money so I can pay Tanya at the same time?
Okay, good. Okay, I'll meet you in my office.
Okay, good, thanks.
J'ai compris, sauf que comme année, c'était la graphique qu'il fallait faire. Ouais, celle-là.
There's a 90-page book that just wants to read. There's a 90-page big ass book that just wants to read.
The what? Probably. I've never visited. I never bought it before. So it should say that everything is, once you go to checkout, it'll add you to shipping. It's probably going to be shipping. Is it, sometimes the shipping is really cheap because they're just putting it in an envelope. You're going to have to see. Just go all the way to checkout and see what the price is, because you don't have to buy it if you find the shipping too high. Donc,
je pense ce problème-là, mais je ne sais pas de
Ah, ok.
On prend ça en compte, là, au début, avec,
On a le temps, puis d'accord. Il y a du monde.
Ouais, techniquement, dans le
pour les derniers problèmes.
Genre, je comprends pas pourquoi quand je tourne de
Il me
même.
semble que c'est plus compliqué que
Ah, ouais.
non, parce que quand on rentre,
Ça va être comme ça.
malgré, par exemple, mettons, ça se prend à
Il y a une fois qu'on est arrivé par
puis
l'est.
c'est ça, et au remonte. C'est comme,
Dans le fond,
dans le dernier examen, il est non, dans la question, on dit pas que ça traverse. Si ça traverse,
Non, mais
ça
on a la mer en fait.
si ça traverse pas,
C'est correct.
ça dit
Gestion.
into the
Genre,
coil,
tu comprends pas, j'ai fait ça.
je dirais jusqu'au point que.
Moi, puis alors, se regarder, puis on
Ça,
partait
c'est
à rire.
oui.
Genre,
60% c'est ça, mais lorsque c'est rendu au milieu,
Let's do this problem. Tu me répondras pour lui. Attends, je vais juste
les
passer.
deux autres, genre, il y en a un qui n'est pas répondu. Mais c'est l'autre, les frères, je pense qu'ils sont
So bar magnet is drop, donc ça fait tout le long.
Ah, moi, dans le test SQ,
C'est ça, c'est ça.
plus les points positifs, ça donne 52 points.
Then, top one? Yeah, okay. So c'est yeah. Jusqu'à quand?
Non, non, ça me fait vraiment.
ça,
65, là.
ça,
Je pensais avoir 20%, fait que j'étais là.
ça va.
52, c'était genre.
Jusqu'à le sang, t'es là?
Ouais, moi, j'allais me coucher. Mais
je pense que ça va ralentir l'augmentation, mais ça va continuer à augmenter un peu jusqu'à la moitié, peut-être pas la moitié.
Non, t'as raison.
Yeah. Et en fait, je me demande si c'est une gestion un peu abstraite, là, mais je fais juste ça bizarre qu'en augmentant le flux, ça crée un courant. En fait, je trouve ça bizarre que l'électric field puisse créer un courant. Je me demandais c'était quoi le.
C'est pas le magnetic field qui crée le courant. C'est vraiment, on a besoin d'un magnetic field. Et comment est-ce qu'on a produit? Avec un courant.
C'est ça, mais je comprends comment ça s'en produit.
C'est inertia. C'est comme une loi physique. On dit que la nature oppose toujours le changement. Donc, c'est comme, est-ce que tu as déjà vu l'expérience? On le tient, on le tient. Donc, tu vois, le roue spin dans ce sens-là, okay, dans le sens de l'axis, mais ça tourne sur lui-même parce que la nature n'aime pas qu'il va y avoir un mouvement négatif du roue. Donc, ça va opposer le changement du motion. It's going to oppose the direction of the motion by creating a counter torque to the wheel. It's just a matter of it's called moment of inertia. I have another example for you. Okay. On augmente la superficie d'un double pour faire un IMF. But, yeah, exactement, c'est la même chose. Donc, on peut voir. Donc, si on augmente la superficie, qu'est-ce qui va arriver? Il va y avoir plus de field lines vers le bas ou vers le haut? Il va y avoir plus de field lines vers le bas, donc il va y avoir un induction vers le haut. Donc, ça veut dire que le courant va faire ça. Oui, mais on augmente le flux. Il y a un changement de flux.
Ouais. C'est la corde avant.
Ouais. Voilà. Est-ce que tu as déjà fait un fidget spinner?
Non.
C'est quoi? C'est quoi? Est-ce que tu peux en avoir un de vos amis?
Non, je pense.
Take one and spin it and try to turn it like this. And you'll see that there's a resistive force. That's inertia. Because it's not wanting you to resist the force, so it's going against your motion. It's cool.
Okay.
Yeah.
Merci.
Okay, bye.